In the compressible flow, normally we use the stagnation property. So for stagnation property, we'll consider here a fluid flow which is taking place from section 1 to section 2. So this one represents the state 1 and this one represents the state 2. At state 1, we have pressure equal to P1, temperature equal to T1, density equal to rho 1 and the velocity equal to V1. So these points are called as static point, or these are called as static property. At point number 2, we have a velocity equal to 0. In that case, it will be called as a stagnation point. So the stagnation point is that point at which the velocity is brought to rest adiabatically reversibly. And this point, instead of representing by suffix 2, is represented by suffix 0, 1. So two suffixes are normally used in the case of stagnation. The first suffix indicates that it is the stagnation property of the static point 1, that is 0, 1. If this point is 2, then the stagnation property will be correspond to 0, 2. Velocity will be equal to 0 here. So we have V01 is equal to 0. So this static pressure will convert into a stagnation pressure equal to P01. Temperature T1 will convert to stagnation temperature T01. Static density ρ1 will convert into stagnation density equal to ρ01. So this property we are interested, which are called as the stagnation properties. So here, since the fluid is moving from 1 to 2, we'll apply the steady flow energy equation, which is Q plus H1 plus 1 by 2 V1 square plus GZ1 equal to W, that is the specific work, plus we have H01, enthalpy at point number 2, hereafter will represent by 2 suffix, plus 1 by 2 V01 square plus GZ01. Now because it's a adiabatic flow, Q will be equal to 0 and there are no moving parts, so work will be equal to 0. The changes in the potential energy is neglected, so Z1 is cancelled with Z01. If we assume it is a perfect gas, then enthalpy H1 we can write as CpT1 plus 1 by 2 V1 square, where V1 is the velocity at point number 1 equal to H01 we can write as Cp into T01 plus we have 1 by 2 V01, but V01 equal to 0, so second quantity will be equal to 0. So in this fashion we can find out the relation between the stagnation temperature and the static temperature. So we have Cp into T01 will be divided by Cp, so entire equation will divided by Cp into T1. In that case we will get T01 divided by T1, Cpt1 divided by Cpt1 is 1, plus we have 1 by 2 V1 square divided by Cp into T1. Already it is known here that Cp value will be equal to gamma times of R upon gamma minus 1. So we have the product is Cpt1, so we have Cp into T1 will be equal to gamma into R into T1 divided by gamma minus 1. And we have one more definition of the velocity of sound, which is equal to under root of gamma times RT1. So we can replace this product as CpT1 will be equal to this term, that is gamma RT1 will be same as C1 square, that is the velocity of sound at temperature equal to T1 divided by gamma minus 1. So this substitution will do here. In that case we have T01 divided by T1, that is the stagnation temperature divided by static temperature equal to 1, plus Cpt1 is, we have to write down here reciprocal, will be rearranging this term, will get gamma minus 1 by 2 V1 square divided by C1 square. But we know that V1 by C1 is nothing but the Mach number, so we have T01 divided by T1 equal to 1 plus gamma minus 1 divided by 2 into Mach number 1 square. So this is the relation between the stagnation temperature and the static temperature. T1 here is called as static temperature, T01 is called as stagnation temperature, and in between this we have a relation is 1 plus gamma minus 1 by 2 into Mach number 1 square. If we know the ratio of the T01 and T1, like this ratio, we have T01 by T1 will be equal to P2 by P1 to the power gamma minus 1 by gamma. So we have a similar relation can be generated for stagnation pressure, which is P01 divided by P1 will be equal to same as T01 by T1 to the power gamma upon gamma minus 1, and T01 by T1 is 1 plus gamma minus 1 by 2 Mach number 1 square, and whole power is gamma upon gamma minus 1. Similarly, we can write the density relation also, which will be equal to rho 01, that is the stagnation density at point number 2, which is equal to 01, is divided by static density rho 1 will be equal to 1 plus gamma minus 1 by 2 Mach number 1 square. Now here is gamma, and this power is cancelled, and we left here with a power equal to 1 upon gamma minus 1. So these relations are used to convert the static property into stagnation property. We can represent this stagnation property on TS plot. This entire process is an isentropic process. So first of all, you have to locate the state 1. So this one is state 1. Correspondingly, we have pressure equal to P1, temperature equal to T1. Now here, as per this equation is considered here, T01 is more than T1 by difference of 1 by 2 V1 square divided by Cp. So from this point we have to move upward to show the stagnation point 01, and during this process entropy remain constant. So this point here represents 01, and we have S1 is same as S01, that is a process is isentropic process, constant entropy process. The corresponding pressure is called as stagnation pressure, and the corresponding temperature is called as stagnation temperature T01. And this difference between the stagnation and the static temperature is given by V1 square divided by 2 times of Cp, that is this term. This is called as dynamic temperature, this is called as static temperature. This one is called as stagnation temperature. This one is called as dynamic temperature. Now whenever we have Mach number equal to 1, the corresponding properties are called as critical property, and they are represented by asterisk. So we have T01 by T1 equal to, you have to put here Mach number equal to 1. So if you put here Mach number equal to 1, we have a simple relation is T01 by T1 equal to 1 plus, and let assume here gamma equal to 1.4. So we have 1.4 minus 1, that is 0.4 divided by 2, that will be equal to 0.2, and Mach number equal to 1. So if you take a reciprocal of this, that will be called as critical property is T asterisk divided by corresponding stagnation temperature will be reciprocal of 1.2 will be equal to 0.833. So remember this relation. When we have Mach number equal to 1, then the critical properties T asterisk divided by T0 is 0.833. Similarly, we can develop the relation for P01 by P1 equal to 1 plus, this term is same as 0.2 to the power. This gamma upon gamma minus 1 will become 3.5. In that case, we have critical ratio P asterisk divided by stagnation pressure P0 will be equal to 0.5283. For this, you have to select Mach number equal to 1. Similarly, we have rho 01 divided by rho 0 will be equal to 1 plus gamma minus 1 divided by 2 Mach number will be same as 0.2. This time power is 1 divided by 1.4, that is 0.4. In that case, we have the density divided by stagnation density at a critical point will be equal to 0.6339. This ratio we can confirm. In generalized form, we can write this equation as T0 divided by T equal to, if we only use gamma equal to 1.4, then this value will be equal to 0.2, and we have Mach number square. So in generalized form, this equation is 1 plus 0.2 into Mach number square. Similarly, we have P01 or simply P0 divided by P equal to 1 plus 0.2 into Mach number square. We have power is gamma upon gamma minus 1 is same as 3.5, and we have rho 0 divided by rho equal to 1 plus 0.2 Mach number square. Ratio is 1 by 0.4, that will be equal to 2.5. So these are the standard relation in terms of Mach number, but this time we have gamma is equal to 1.4. And these are the relations which are called as critical relations, when which Mach number equal to 1 and gamma equal to 1.4. That is, these relations are valid for air. So here we will take a one numerical based on the stagnation properties. An airplane is traveling with a constant speed at an altitude of 3 km. The stagnation temperature recorded was 27 degrees Celsius. The speed indicator fitted in the cockpit is faulty. Can you help the pilot to find at what speed the aircraft is flying? Assume the atmospheric condition at sea level as 1 bar and 300 Kelvin and the temperature lapse rate as 6.5 Kelvin per kilometer. So consider this one is the sea surface and we have an airplane is flying at an altitude of 3 km. At sea level, we are given the pressure equal to 1 bar, let labeled as 0, and T0 is the sea level temperature equal to 300 Kelvin. The altitude is given as Z equal to 3 km. So this one is the stream here. At this point here, we want to calculate temperature. That will be the static temperature, and here it will measure the stagnation temperature equal to T0. And he says that the stagnation temperature equal to 27 degrees Celsius. That you have to convert into Kelvin. Now if we are able to calculate this static temperature using the temperature lapse rate, then we have a relation between T0 and T. So we have T0 divided by T will be equal to 1 plus 0.2 in the case of air, Mach number square. And we know here the Mach number is given by V by C. For this one, if we know the velocity of sound, which is given by under root gamma RT, we are able to calculate the velocity of flight. So this static temperature at altitude equal to 3 km, we can calculate using the relation T equal to T0 minus lambda Z, where T0 is the temperature at the sea level, which is equal to 300. Lambda is the standard temperature lapse rate, which is taken as 6.5, and we have altitude Z equal to 3. So we know the static temperature at the altitude equal to 3 km is 280.5. Once we know the temperature at this altitude, we can calculate the velocity of sound using the relation under root of gamma RT. This time the working fluid is air, so we can take gamma equal to 1.4, gas constant equal to 287, and the temperature at the given altitude. Remember to take static temperature only, that is 280.5. So velocity of the sound will be is 335.7 meter per second. Now we know the velocity of sound here. Now this time we'll apply this equation, that is the ratio of a stagnation temperature to static temperature equal to 1 plus gamma minus 1 by 2 Mach number square. So we have T0 divided by T equal to 1 plus 0.2 into Mach number square. We have stagnation temperature equal to 300. We have a static temperature T is equal to 280.5 equal to 1 plus 0.2 into Mach number square. So if we solve this, we will get Mach number equal to 0.589. Now once we know the Mach number, we can very well calculate the velocity of the aeroplane, which is V by C. So we have V is equal to 0.589 multiplied by the velocity of sound, which is 335.7 equals to 197.92 meter per second. Multiply 3.6, we will get kilometer per hour, is 712.5 kilometer per hour. So you can very well help the pilot what is the speed using the simple equations. That is, one equation is the stagnation temperature, second is the Mach number, and one is the velocity of sound equation. Determine the maximum temperature encountered by the skin of a supersonic fighter aircraft flying at an altitude of 6 km. The speed of the aircraft is 2000 km per hour. Assume atmospheric condition at a sea level as 1 bar and 300 Kelvin and the temperature lapse rate as 6.5 Kelvin per kilometer. So let's assume here that this one is the sea level. At sea level we have given the pressure, which is represented by P0. equal to 1 bar, temperature T0 equal to 300 Kelvin, and the altitude of the airplane is Z equal to 6 kilometer. So this one is a stream. When this stream will strike on the skin, that is on entire surface here, it will become a stagnation temperature equal to T0, and let's call this one is T. So to get this idea clear here, I will call this one is T1 and this one is T01. So T1 is the static temperature and T01 is the temperature encountered on the skin is the stagnation temperature. And this time the flight speed is known. Since the flight speed is same as the velocity at point number 1. Velocity at 1 will be equal to 2000 km per hour. So this time we'll use the relation between the stagnation temperature and we can calculate here the stagnation temperature. But before this, first of all we'll calculate here what is the velocity of sound using the equation under root of gamma RT. And since we know the velocity, we can calculate here the Mach number m1, which is equal to v1 by c1, and then we have finally t01 by t1 equal to 1 plus gamma minus 1 by 2 Mach number 1 square. Using this, we can calculate the temperature at the skin of aircraft. To calculate the temperature at the altitude of 6 km, we'll use the equation T equal to T0 or T1 equal to T0, that is the temperature at sea level minus lambda multiplied by Z. So we have T1 equal to 300 minus 6.5, which is the temperature lapse rate, and altitude is 6 km. So this temperature is 261 Kelvin. Now we can calculate corresponding velocity of sound C1 using the equation under root of gamma RT1. Our model is air, so we have gamma equal to 1.4, gas constant equal to 287, and the temperature at altitude 6 km is 261. Always remember to calculate the velocity of sound using the static temperature, not the stagnation temperature. Is 323.8 meter per second. Now we can very well calculate Mach number, which is v1 by c1. We have v1, you have to convert into meter per second, so we have 2000 divided by 3.6 divided by the velocity of sound is 323.8. In that case, we will get Mach number equal to 1.71. And finally, we will use the equation of a stagnation temperature relation, which is T01 by T1 equal to 1 plus gamma minus 1 is same as 0.2 Mach number square. So in that case, we have temperature encountered by skin will be equal to T1, which is same as 261 into 1 plus 0.2 into Mach number 1, which is 1.71 square of it, will be equal to 414.62 Kelvin, that is 141.9 degree Celsius. Now this is supposed to be very large, and therefore in a fighter plane the nose is kept as a very small nose, because the heat transfer here is directly a function of the area and the temperature. Since the temperature is higher, we want less heat transfer, so you have to keep the nose as pointed nose in a fighter plane. In a flowing gas, a thermometer is inserted, whether this records the true temperature or a stagnation temperature. Find the temperature at the front nose of a bullet at a sea level with a Mach number equal to 1.2. So consider here a duct, and in this duct the gas is moving with a velocity equal to V1 and the true temperature of gas is T1. When this stream will strike to the bulb, it will record a temperature equal to 201. That is the stagnation temperature. So this time the thermometer will measure the stagnation temperature rather than the static temperature. So this temperature T1 is called as true temperature. Any attempt is made to measure the temperature of flowing gas with the help of thermometer, it will not measure the true temperature, rather it will measure the stagnation temperature. So any attempt is made to measure the temperature of flowing gas, it will measure the stagnation temperature and not the static temperature, that is the true temperature. But we can very well calculate our true temperature using the relation we have T01 by T0 equal to 1 plus gamma minus 1 by 2 Mach number square. For this one, we should know the velocity of the fluid and the velocity of sound. From Mach number, we can very well calculate the static temperature T1. In the second part, he says that find the temperature at the front nose of a bullet at a sea level with a Mach number equal to 1.2. This time we are given the bullet and the Mach number of the bullet is given as 1.2. We are interested to know what is the temperature on the front nose, that is the stagnation temperature at point number 1, and correspondingly on the sea level we have a static temperature T0. Now this time the static temperature is not given at sea level. We'll take this temperature equal to 300 Kelvin. And using this equation, we can very well calculate the stagnation temperature. So in that case, we'll get the stagnation temperature, which is the tip of the bullet, is given by T01 equal to T1 into 1 plus gamma minus 1 by 2 into Mach number square. We have static temperature T1 is same as 300 into 1 plus, we assume the air property, so gamma is 1.4 minus 1 by 2 is 0.2 into Mach number is 1.2 square is 386.4 Kelvin, which is close to 113.4 degrees Celsius. So once the bullet is fired, normally the tip is get blackened because the temperature rise is very high, is 113.4 degrees Celsius. A Schiller photograph of a bullet show a Mach angle of 40 degree. So this time we are given the alpha, which is equal to sine inverse of reciprocal of Mach number is equal to 40 degree. So indirectly we know the Mach number. Pressure and density of the undisturbed fluid flow, that is at the static condition, we have P1 equal to 101.3 kilopascal. And the temperature at this point is T1 equal to 10 degrees Celsius, which is equal to 283 Kelvin. What we are interested to know, what is the approximate temperature at the nose of bullet. So if the bullet will fire like this, so this temperature we want to know, that is T01. We know the static temperature, we are interested in the stagnation, and indirectly has given the Mach number. So we have 1 by m, this is sine inverse actually. We have 1 by m equal to sine of 40. In that case, we will get the Mach number equal to 1.56. Since we know the static temperature, we are able to calculate the stagnation temperature T01. So we have T01 by T1 equal to 1 plus gamma minus 1 by 2 Mach number square. So we have T01, we interested to know T1 is same as equal to 283 equal to 1 plus. We'll take gamma equal to 1.4. So 1.4 minus 1 divided by 2 is 0.2. And we have Mach number is 1.56 square of it. So we can calculate the stagnation temperature T01. That is very close to 420 Kelvin, which is approximately equal to 147 degrees Celsius.